Hello. Today we're going to be presenting our research in the RU program on the fish project. So why is this project important? It's critical to ecological and environmental studies to prevent overfishing, to study migratory patterns of fish due to dams, and to classify endangered species and new species. Some of the problems faced without having this automated is it requires a lot of man hours, which is a lot of time and cost, and the image quality isn't so great because of lighting and water conditions. The results that we expect to get from this project were to get a fully functional algorithm to classify and count fish species based on underwater camera observations, and then classifying fish based on unique characteristics. First, we had to implement background subtraction. The background is the foundation for the entire project. So the better quality background that we can get, the higher quality images of the fish we could get as well. Some of the methods we tried were averaging and filtering, and stereo vision, and a statistical approach. For the averaging and filtering method, we detected the background image by averaging multiple frames together, and this included low-pass filtering, and then we extracted static objects. Then we subtracted the image from the detected background, and we detected the silhouette of the fish through thresholding and a square method. After averaging all the frames together, this is the background that we got. Some of the problems are that we assume that the background is static when it's actually not, and also sometimes a fish would stay in one place for a long period of time. So if you look closely, you can see that that fish appears in the background image. So after we had the background and we did the subtraction, we got the image on the top left. Then we thresholded the image using a positive and negative index for the intensities, and we got the image on the top right. Before we tried not using the negative threshold, and we didn't get the fish in the upper right, but we also didn't get the shadow underneath the fish in the lower right corner. So then we tried erosion and dilation, and those are the results for those. So then we tried to improve the outline detection by using a square method. First, we had to heavily dilate the image so we could isolate each fish. So that's a picture of the isolated images of the fish. Next, we had to place a square around pixels that were in question. For our examples, we used a square of size 31 by 31. We just divided the square into 4 quadrants, and if there was a significant amount of white pixels in each quadrant, we changed the pixel in question to white and included it as part of the fish. On the right is the results from using the square method. Next, we had to extract the outline, and those are results from the outline detection. The advantages of this square method is that no dilation or erosion is required, so it leads to a better outline. But some problems are the outline's a little like rigid in places, and it's not the best outline because we don't have a great background. So some of the problems with this method are a static background is necessary for the averaging. However, with the underwater conditions, this isn't possible because of many things moving. So then, for the thresholding, when we use the negative index, we got the shadow underneath the fish, which is a problem as well. And we also tried automatic thresholding, but this didn't work out so well. The techniques also aren't transferable. It only works on single images, and it may not work on other sequences. Okay.
After we did the averaging, we found that we could obtain a better result than what we had obtained. So one of the methods that we were planning on implementing was the stereo vision. When we got this sequence of images, it came with two files per image, a left and a right, which we can use them to obtain a 3D image of the fish. It requires a lot on math, as you can see over here. IL and IR are going to be the right image and the left image. And then you're going to go ahead and create create your 3D object. And then in order to extract the object from the outline, you were going to have to, it uses the 3 planes because it's 3D. So whatever the vertical plane was, you would assume that that is foreground instead of background, and you would be able to subtract that and obtain that foreground object. It requires a lot of distance and reference points. You create reference points in each image, the left and the right image, and then when you overlap the 2 images, you use the reference points to sync up to obtain your images. And this is kind of a description of how it works. You have your left image and your right image, and then you're going to create your reference points. And then once it overlaps the reference points, you can see on the image on the right that it's by distance, and you can see where the red is the closest and the blue is the furthest. So you can see in how the starts at red in the bottom. But what that does is it creates a vertical axis also, and so you can see how the car is a different color than its background, and you would be able to extract that. We did not implement this method. We did a lot of research on it, but did not implement it because we did not have enough information, and it required resources that we did not have. You needed information on the camera used and the distance between the cameras and things like that. So we could have guessed, but we would not have been able to accurately recreate the 3D objects in order to finish the stereo vision. In the future, if we are able to obtain that information and we are able to obtain the necessary MATLAB components, it would be possibly beneficial to implement the stereo vision method. It looks pretty promising. So a third approach that we plan on trying is the statistical detection of the background. Just a basic outline of what we're doing is the process of background detection based on discrimination functions obtained through analyzing the geometrical structure and spatial configuration of well-defined pixel intensity distributions. Basically, what we're going to do, what that's saying is we're just going to observe each pixel in an image represents an intensity, and so we're just going to observe the intensity values, and from that be able to analyze them and where they are for the spatial, what shapes they're in, what they look like, and from there, after reviewing a sequence of images and observing different pixel intensities in those images, be able to determine what is background and what is foreground, and then use that determination to continue subtracting through the rest of the frames. Basically, so it's based on the multiple frame sequence, so you're going to look at multiple frames at a time. And the first thing you're going to do is you're going to use the intensities, the pixel intensities, and the values that are represented in the image, and you're going to subtract or obtain the PDF of that background. And you can use this using histograms. And then the next thing you're going to do is use a mathematical model to obtain the threshold. And from there, from obtaining the threshold, that is what's really going to allow you to represent foreground and background. Just a little background on the statistical method or a base knowledge of the statistical method that's required in order to complete what we're going to do. It's basically hypothesis testing. You have two signals, you have a signal and noise. Basically, our signal is going to be our background, and our noise are going to be the fish swimming throughout or the seaweed moving or anything like that that could possibly interrupt our background image. So what you're going to do is you're going to set, so if you look, you'll have your image and your background, and then you'll have your noise. And so anything that's here, you'll classify as your image, and anything over there, you'll classify as your noise. But this area in the middle is your probability of error. And in this, in our fish images, you will have a higher probability of error. But what you want to do is you want to be able to set you want to get the probability of error as low as you can, and then you want to be able to set that. There's two types of errors: a false alarm and a false detection. False alarm is saying, you have the false alarm and the false detection, and you're going to want one error more than the other error. In our case, we're going to want we would prefer to have a false alarm than a false detection. So that just means that we'd rather say that something is a fish and then later on be able to extract it using classification, and then in classification not be able to classify anything and then throw the image out, than to not detect a fish at all. So using that, go back to the previous slide. Using that, you're going to have your probability of errors, and you're going to be able to set this threshold, and we're going to want the threshold not directly in the middle. We're going to want it closer to the noise, so that it detects the fish so we're going to detect the background and then subtract the fish. All right. One of the ways that we're going to use the intensities is through pattern recognition and classification. Basically, we did a little experiment to get familiar with statistics and the pattern recognition and the pixel intensity values and how to work with them. What we did was we created an image that was a 4x4 quadrant square, and we are going to use the decision rules in order to classify pixels into which quadrant they belong to, and then try and recreate an image, or try and detect whether that pixel should be, in our case, background or fish. So what we did was we used the distance formulas to do this. Basically, this is a quadrant that we created. It has 4 different pixel intensities in it. It has the black, the darker gray, the lighter gray, and the white, and then we added some noise to it. And once we added the noise, you can see it's very distorted, and that kind of represents our background and our foreground, in that you can see this is our background, and then all the noise are going to be the fish or seaweed moving or anything that could interrupt our background image. And we're going to try and recreate our background by, what we did was we took pixels within the image with the noise, and then we looked at them and we used the distance formulas and the mapping, and we determined whether that pixel we took the pixel and then we looked at its neighbors around it. You can create whatever size matrix you want, and through looking at its neighbors, we determined whether it should classify as foreground or background. In this particular case, you had 4 different signals. You had each intensity value, the white, dark, light gray, and black, represents a different background or foreground or noise. So ours will be a bit different compared to background and foreground. But basically, the third image that we have is what we recreated when we used a 3x3 matrix, and you can see that it gets better as you go bigger. The next one's a 5x5 matrix that's looking at the neighbors around it, the 5-region neighborhood. Basically, to sum up, for the averaging background, which is the one that Philip presented on, that was the one where we basically stacked a bunch of frames and averaged all the pixel intensities for that particular pixel in that location. It was worked out really well. We got a very good background, but we feel like we can improve on that because some of the things that Philip was talking about with the static and how you can't assume that your background's going to be static, and with the fish swimming in and out, and if a fish sits there longer. So in order to improve, we decided to go on stereo vision, but we didn't complete this. There was not enough information to do it and not enough background knowledge. And then so the next thing was the statistical. We reviewed the plan for the statistical detection method, and we're going to use this to try and determine whether pixel values are of foreground or background images, and then use that to subtract the background and leave just the fish, and then send those on to classification. Do y'all have any questions?
When you say you want to use statistical method to detect, to separate background and foreground, do you consider only one image or an image sequence?
Well, there's a big image sequence, and we're going to look at the first, I don't want to say few images, but the first, we're not really determined how many images we're going to need in order to complete it, but we will look at multiple images in order to determine what the pixels belong to.
Okay, and back to your example with, I think, 4 squares, and then adding some noise. Can you go to that slide? And here, for instance, you say the foreground is like those noise, those like some kind of pepper, salt and pepper type of noise. And then when you consider like extracting fish within the background, do you consider the size of the fish you're looking for, or maybe you applying some statistical model for that?
Well, we're going to create this as the mathematical model in order to classify, but basically we're going to we're going to look at an image as a whole, or a sequence of images as a whole, and look at how their pixel intensities change, and look at the different areas of the image, and you can kind of tell this area over here is an object because of the pixel values around it, and you can tell the area in the top right corner that could be an object. All of this over here is all the same color, so that might all be water, and then do something like that to compare multiple images and get a good idea of like the geometrical and all that, the spatial, and then try and from there create a mathematical model in order for the program to continue doing that.
And also, do you have any plan for testing whether a particular statistical model will work, or how are you going to measure that? We've outlined a couple models that could work. We haven't nailed it down to which model we're going to work. We're going to run some tests on each model with not fish images, with rather more simple images, something like this, and look at we have a list of models that we want to consider, and so we're going to do testing on them to see if it, how accurate it is in simpler images, or images with images that have a similar change to our fish, but not so like noisy and fast, like there's seaweed and fish and everything, in order to test the methods, and then from there pick a method that we're going to use and then implement it. Okay, and I think last thing I want to ask, maybe also better if you can add some comments, that's also fine, is about whether you want to separate fish and background in a static setting, meaning just look at the image and here's the fish and here's not, or you want to have a dynamic, let's say that maybe fish will move from somewhere into your camera view, and then detect that, and then try to apply whatever method you use for background subtraction. Do you consider about these options, like static and dynamic versus dynamic, or probably?
We talked a lot about that in the static versus dynamic, and the problem with the averaging was that we were only trying to detect what was static. And so it didn't work because, it worked very well, but it can be improved upon because, like, as I was saying earlier, like, things underwater change. Like, a fish swims by, and then you can see the sand under it move, and, like, your background is not static. So we were planning on using the statistical method, looking at all of it together in order to create the model for the pixel intensities, but after that we're going to focus on just obtaining the background. Instead of pulling the fish out, we want to just obtain the background, and then once we have a solid background image, send that on to, in the next step, kind of subtract the fish. Sorry.
Yeah, I think another question may be directly related to Philip's presentation regarding the square. You mentioned like a square approach. I think that's maybe
something that you want to look into? Can you be a little bit specific on, for instance, what you did and whether that method has certain advantage or disadvantage?
Well, when we subtracted the image, in order to detect the outline, we had to completely fill in the silhouette of the fish.
Okay.
But a lot of the fish pixels weren't being picked up because of the background not being perfect. But so I tried to basically reconstruct the fish by using the square method and try to fill in all those pixels that belong to the fish so we could detect the outline. I think it could be improved upon further, but I think to get the best results we need to work more with the background because you can't get a very good image with a bad background.
I guess a relevant question is, do you want to consider like maybe the shape, the size of the fish in the outline? Do you want to have some template in terms of the orientation of the fish so that, for instance, when you show some images, certain shapes are fish-like and certain shapes are not? Do you want to consider, for instance, eliminate some non-fish-like type of outlines?
I think we want to pick up those, but in classification, those won't be able to be classified as anything. But we want to pick up anything that should be a fish.
Okay. But do you consider like shape information or orientation of the fish will be important feature to consider in classification?
Yes, but we're only concerned about fish that are on like a side view because we can't really classify fish if they're facing towards the camera or away from the camera.
Yeah. However, with certain fish, there are certain characteristics that can be classified without having the entire fish. One of the fish that the graduate students were working on and explaining, they had a fish that only half of it was in the image, the other half was out of the image, but they were still able to classify that fish because it had a stripe on its tail, and they wrote a classification function in order to specifically look for stripes on the tails of fish. And so by having just the tail of that fish, they were able to classify that and count that fish in the count. So we do, to an extent, look for just, flat fish images where you get the whole image, but also we try to classify everything that could be a fish because in cases like that, you may be able to classify something that with only part of a fish.
I think that's a very important point that you want your background abstraction to also interface with the subsequent
Yes.
processing methods. Okay. And also, another thing, how much time do you envision that you can finish some of these tasks that you think that you plan to do? Roughly.
Probably like 2 to 4 weeks, I would think.
Mhm.
Okay, thanks. Good to know. Thank you. Yeah, okay, thank you very much.